Hello students, welcome back to another lecture of machine learning series. Today we will discuss the well-defined learning problems. So the definition is, a computer program is said to learn from experience E with respect to some class of task T and performance measure P. If its performance at task in T as measured by P improves with experience A. So that means it is a well-defined problem. Okay. So we have, next is, for example, a computer program that learns to play checkers, or another game you can take is chess, okay, might improve its performance, okay, ability to win at classes of task involving playing checkers game through experience obtained by the games played against itself. So that means it is a computer program that is playing by another computer program, it is playing by itself and is improving its game. So this problem of playing a computer program that learns to play checkers might improve its performance, okay, when it is playing by itself. It means that it is a well-defined learning problem, and we can identify basically three things. The first is the task, what you have to do. It is as to learn how to play, and the measure of performance to be improved. So that means if your winning rate is, let's say, 80% or let's say 70%. So if you are playing, your winning rate should improve. It should improve to 75%, gradually it should improve to 80% and so on. And the source of experience. The source of experience is what? You are playing against yourself. Okay. So basically we can formulate this problem, a checkers learning problem, task T, playing checkers, performance measure P, percentage of game won against itself or against opponents. That would be our performance measure. See, in ML, if you are making something, a performance measure, so it should be a number. Okay, so that number can decide if it should be gradually improved. Training experience E, playing practice game against itself. Okay, so we have three things in checkers learning problem. For example, in handwriting recognition learning problem, we have task T is to recognize the handwriting. Okay, and the performance measure P is that percentage of words correctly classified. Okay, training experience E, a database of handwritten words with a given classification, that this is A, this is B, and this is apple, this is water, something like that. And in the case of robots, a robot driving learning problem, that means a task T means that driving public 4-lane highways using vision sensor. This is our task, that an autonomous vehicle is driving through a 4-lane highway and it is equipped with vision sensors. That means the images are fed to the system. The performance measure means the average distance traveled before an error. Error can be just that a human is keeping a watch on that. An error can be a small bump or an accident, okay, or somewhere where the autonomous vehicle is not stopping and you apply a human intervenes and apply brakes to avoid an accident, basically. Training experience C, that is, you have a sequence of images and steering commands. So image is fed and you have to take and steering command, whether you have to keep it straight or move left or right. Okay, and it is recorded with observing a human driver. So you have an image, you are capturing, and steering commands, and human is driving. So that is what your training experience. Okay. Consider designing a program to learn to play checkers with the goal of entering it in the World Checkers tournament. Suppose you are creating a program that is you will play in a big tournament or in a big event. Okay. So we can have direct and indirect feedback. Direct feedback means learns from labeled examples. Okay. Checkerboard states with correct moves, or indirect ways is learns from outcomes requiring credit assignment for past move. So if you have set of 3 moves and you choose, let's say, the second move, so what score you actually get? What score you get? Learners control over training data. So teacher-led, query-based and self-play. So learner relies on the expert selected examples, that okay, learn from this example or that example. Query-based, learner asks for clarification on confusing ones. So specifically learner will play, and whenever it is confused, it will ask for the query. Self-play, learner generates data by playing against itself. So that is known as self-play. So training data distribution. Learning is most effective when training data matches the real world test scenarios. Okay, so it is more effective. Training only against itself may miss key situation encountered in real games. So what basically happens in these kind of big tournaments, for example, if you consider the game of chess, so we have grandmasters coming from each country. They have adopted, they have learned, they practiced through several decades of playing chess, and they have mastered certain techniques, how to defend, how to attack. So if those experiences are fed to the learning program, okay, in those scenarios a program is learned to train, so that would be most effective. Okay, then self-training, because it can miss the key situations. Now final decision, the system will train by playing against itself and maximizing the training data without needing any external trainer. So this is what we are actually in a course to design a checkers playing program. Okay. So we can formulate this checkers playing problem. So first we'll identify task T, then we'll identify performance P, and then we have experience E, training experience E. So task is simply playing checkers. Performance measure P, we can calculate in terms of percentage game won. Training experience E, the game played against itself, that is your training. So if you want to complete this design, what we have to do is basically we have to choose the exact type of knowledge to be learned. What you have to learn should be explicitly clear. And when you are formulate a problem, okay, with these 3 measures, so that means you are clear that you are able, and you can choose what ML techniques, what the problem is, how you can get a solution, you can choose that. So that is why we are discussing this topic. The representation of this target knowledge, how you will represent that target knowledge. For example, in checkers, there could be board states. Similarly, for chess, it could be a board state. Okay, so we have board states. And then we have to choose a learning mechanism. How you will learn. Learning mechanism means we can choose LMS, gradient descent, and so on. We'll take these not in detail but in brief while discussing this topic. The idea is we are designing a checkers playing program or checkers playing module. So it should be ML based. So our learning objective of this program is to learn the legal moves. Okay? Common in optimization problem like scheduling and process control. So we have to have clear cut-off learning objectives. Then we should know the target functions. What is my target function? So choose a move is one type of a function which we can have in this particular situation. Another one can be the target function V. Okay? So directly selects the best move, but that is hard to learn. And B gives R, that is assigns a numerical score to board state. So this is very easy to learn. Okay? So we can have this B to R. That every state will have a numerical value. So that we can give numbers, and through those numbers we can decide what to do. So we can define VB, okay, for a board state. If you have a score of 100, so you win. If you score a minus 100, that means you lose. And draw is if your score is 0. And there could be some non-final state, because when you start playing a game you have not actually lost. You can win or you can lose. So there are intermediary states. And that means we have intermediary board scores. And we can have intermediary values. So non-final state is defined as VB equals to VB dash, where VB dash is the best achievable final state assumption assuming optimal play. Okay? So choosing the target function, how we choose the target function. So basically there are challenges in actually choosing this target function. The first one is that requires searching all possible moves until the end of game. So the search space is very humongous. It's very big. And in that search space we have to select the best possible move unless and until we win. So we have to keep on searching the best possible moves. Not feasible for real-time decision making. Of course, it is not feasible, because when you are searching a large space, you consume a lot of time. Okay? And if your search problem is not linear, so you can have exponential, you require exponential time to search. That is also possible. So termed as non-operational definition. Okay. Then we have to do function approximation. The goal is to learn the operational form of V for the practical use. That is, practically we have to choose the best move under the given constraint, let's say time. We cannot take infinite time, or we cannot take 10 minutes for a move. The other player may get bored. Okay, he can leave. So your learning task will be left uncompleted. The learned function is an approximation of ideal V. So because it is an approximation, because you have taken a decision under certain constraint. So it is not an ideal V, but it is somewhat near or closer to the ideal V. V is your function, learned function. Now, for this target function, you have to choose the various representations. Okay, the options are that function C, various options exist for representing the function C that the learning process will learn. We'll see that those options available in next coming 2 slides. Possible representations: a large table, rule-based system, quadratic polynomial, or an artificial neural network. network. So what we can do is we can make a target table, or we can have some rule-based system, or we can apply ANN, or we can choose any polynomial function to represent our target function. Trade-off is that more expressive representation, the approximate V is better, but requires more training data. So if you have a complex representation of the target function, that means that you can achieve a better V, a target function. But the problem is you require more training data, because all the complex polynomial, let's take a higher order polynomial. So all these states, all the representations should be there. Okay. For example, in this particular situation, we have taken 6 features. The feature number 1 is the number of black pieces on the board. How many pieces you have? X2, the number of red pieces on the board, the opponent, let's say. The number of black kings on the board, X3. X4, the number of red kings on the board. X5, the number of black pieces threatened by red. And X6 is the reverse of number of red pieces threatened by black. So you consider this X5 and X6. If the value of X5 is more, that means red is attacking and you got 2 defense. And in 6, the situation is reverse. You are on the attacking better position if you are attacking more pieces of red. Clear? So our learning program will be represented as CB as a linear form of these functions. Okay. Now, these functions cannot be taken in summation order like x1 plus x2 plus x3, x4 plus x5 and x6, because there should be some, because each function is different. So we have to add certain weights. Weights means we will give them some coefficients. Okay. We will give them coefficient. And remember this from the previous slides, the target function is a combination of from x1 to x6, okay, with some coefficients. There could be more, much more than, you can make x7, x8, okay. And in every situation, there would be one feature that would be dominating over the other. So let's say we have formulated a representative of a target function, w0 plus w1 plus x1, that is we are giving coefficient weights, w2 x2 plus w3 x3 plus w4 x4, w5 x5 and w6 x6. So our target function is a combination of x1 to x6 with some initial weight initialized to it. Okay. So where w0 to w6 are the numerical coefficient or weights to be chosen by the learning system. So the learning algorithm will choose the weights. Okay. And that choosing of weights we call as training. We call as training. Okay. The learned values for the weights w1 through w6 will determine the relative importance of the various board features. If w1 is towards near to 0 and w2 is much higher than 1, okay, so that means this particular feature on that particular board state is insignificant. Okay. Determines the value of board, whereas the weight 0 will be providing an additive constant to the board value. Okay, so every function has some value to begin with. Now, so in the part of partial design of checkers learning program, the task is playing chess, checkers, performance means percentage of game won, training experience E, game played against itself, and the target function is this one. So we have actually formulated a target function. This formulation of target function depends upon the particular problem at hand on which you are working. It is not a universal rule or universal method to actually choose the same kind of target function. But for every learning problem, you should have some target function. Okay, so we have to learn the target function f, we require a set of training data or training examples, each describing a specific board state B and the training value that we call as VB train. This is V train B. Each training example is an ordered pair of form a board state and V train B. So this tuple is an ordered pair. For instance, the following training example describes the board state B in which black has won the game. The note is x2 equals to 0 indicate that red has no remaining pieces. Okay? It has no remaining pieces, that means the x2's value is 0. So black has won. And for which the target function value VB train is therefore plus 100. You remember from the previous slide, if you are winning, it is plus 100, you are losing minus 100. It is a draw, that means VB is 0. Okay? Now, so we have to estimate the training values. So, training information, learner only knows if the game was won or lost. Challenge is assign a score to intermediate board state is unclear. Unclear in sense, when you start playing, there could be a situation where you are actually losing the game, and with choice of correct moves, you can reverse the situation. It is applicable for the black side and for the red side. It is applicable in the both. So issue is the loser doesn't mean all the board states were bad. Early moves could be strong. Okay. Estimate training value of the board state B as V successful B using the current approximation V. And the justification is works well if V is more accurate for the states near the game end. It will be more accurate. Okay, in the intermediate state of the game, it may not be that much accurate. So, convergence means under certain condition the iterative method converges to perfect V train estimates. Rules of estimated training values is VB train is less than minus V successor of B.